This is lab 2 involving motion of falling objects. Here's a brief table of contents of what will be covered in this video. I'll start with an introduction. The purpose of this lab was to observe the motion of an object that is dropped from rest and falls straight down. Then compare this data to two models using Newton's second law to show the effect of gravity and drag on the object. One model will include just gravity, and the other model will account for drag. This should prove the validity of Newton's second law to real-world scenarios and also highlight the concept of terminal velocity. It was a pretty basic setup. I used my iPhone camera to film me dropping a soccer ball from my height and putting this video on the tracker to get the basic position versus time data. Then this original graph from tracker is compared to the two simulated models in an Excel graph showing all three curves in a scatter plot. Here is Newton's explanation of Newton's second law, which we derive from change of momentum over change of time equals net force. From that, we can get these equations here: the velocity update, velocity final equals initial plus net force divided by mass times change of time. To predict the velocity based off of net force. And in this lab, since there's only gravity and drag forces acting on the object, we can use this equation to predict the position below. Since the net force is constant, we use the velocity calculator from the previous equation in this position update equation here. And then the gravitational force for the net force is sort of this formula for weight. And the drag force is calculated by this formula involving the drag constant times final velocity times the j vector. And the net force will be that gravity plus the drag force, so this value plus that one. And just a note that the j hat value is the unit vector for the y-axis telling us what direction is up, 010 meters in the experiment. Next, I'll show the tracker video for the ball falling. As you can see here, I held it from rest right at my head, just dropped it straight down. Obviously, it's not perfect. As you can see, it doesn't fall straight down. There could have been other factors involved too, besides gravity, drag forces, but we're just going to assume those were non-existent for the sake of the experiments. As you can see here, the axis, you have obviously the y and x right here. I had it falling from the positive y down towards the origin, and that's the total distance. That's my heights there for reference. Then I was able to make the model. All we needed was this data here collected, the position versus time from tracker, and the equations from before that I went over there. And the data from tracker was this: the mass of the ball was 0.43 kilograms, so starting time t equals 0 seconds. Starting position, y equals 1.708 meters, and initial velocity of 0 starting from rest. So with that data from tracker, we can now go into the simulated models on GlowScript. And so for this first one, just given the base code for the experiment, we had to make a couple changes. We had to change the ball's mass right here. We changed the initial position to the 1.708 calculated from tracker. Keep the velocity at 0 because it's coming from rest. Keep the j hat there. And then b equals 0 because there's no drag. And then we changed the time to the final time recorded in tracker. And then here we had the equations I discussed earlier for weight and drag force, which eventually gets you net force as well. And then if we run this, we'll see there's only one arrow for one force, which is gravity on the ball at the time. And as you see, the position time graph is similar to one of tracker. I'll show a little bit more in depth of that in a minute. And the velocity time, you can see here with all the data points, which is also similar to tracker. And then for the second scenario, which is where drag was involved, we had everything was the same except for this b value, which I made 0.11, just kind of just testing and checking to get a close final position between both parts of the experiments. And then from this, when we run the program, we see an additional arrow as the ball goes down. In addition to the gravitational arrow, we see this blue arrow for drag force, which we'll see momentarily. There it is right there. And the position time is still the same or similar to as we'll show in a minute. But we see this velocity time kind of start to curve a little bit, which hints at this concept of terminal velocity, which we'll discuss in a little bit. Now we see the comparison between the tracker and the model and this, Excel sheet over here. As you see, they're all initially close at the start. We see the orange dots are the tracker, the gray is the GlowScript with drag, and the blue is the GlowScript with no drag. The with drag is extremely close to the tracker data, and the differences could be because of observational error in tracker or unknown forces such as airflow and other factors. As you see all the data points here, there was obviously way more data points in the computer simulated model than in the actual tracker, but we see these relationships are very close to each other on the plot. Next, we move into this what if scenario if the ball was initially thrown downward. And first, just to expand on that, what we saw last time with the velocity time graph kind of leveling out, we'll change the delta t to have more frames and make it just kind of go a little faster. And then we'll change this initial velocity vector, as we can see here, to kind of get closer to a flattened velocity time graph. And we see it's the same, virtually the same value, this negative 4.21 in magnitude of the velocity. It continues to level out at this, which would be this would be the terminal velocity, as the effects of gravity and drag have canceled each other out. And if we compare this to a negative starting velocity, compare this to a -5, as we see here, just throwing the ball the other way initially, we run it. The position time slightly changes, but we see different shape of the velocity time graph, but with this same -4.21 value, which kind of proves that the terminal velocity stays exactly the same, which is the time and when the drag and gravity are canceling each other out. And as we see here, these are the two snapshots. And just to conclude, this lab was conducting the study of the motion of an object dropped from rest that falls straight down. After comparing the tracker data to different simulated models, we can examine the effects of gravity and drag on the object. We're also able to see the terminal velocity of the ball involving these forces at hand.